Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to go ahead and summarize the last several lectures by looking at some of the key elements of the type of solids that form and what their various crystal structures look like. So let's go ahead and take a look first at our four major types of crystals. So these are often distributed based on the type of cohesive forces. So for example, network solids or covalent crystals and ionic crystals tend to have very strong cohesive forces, so either coulombic or covalent bonds. This tends to make them very hard, but it tends to make them fragile when under stress. So for example, you can crack a quartz crystal or most salt crystals with a hammer. However, they can become strong enough that you get something like diamond that doesn't break easily, but when it does, it tends to shatter along a crystal line. Somewhere on the other end, we have molecular solids. So these essentially are mostly held together by van der Waals forces. So these are a lot more flexible. And as a result, they tend to be a lot softer and have lower melting points because they can be disordered under high heat. Now, metallic structures tend to be quite widely varied, and this is because the strength of metallic bonds themselves can be quite widely varied. They can look more like covalent bonds, or they can only be as strong as, say, dispersion forces. So expect something like iron to be much stronger than, say, sodium. However, the big unifying theme with metallic bonds is because they're in such close contact and they share electrons, they tend to conduct heat and electricity very well. Now let's go ahead and look at these same sort of structures, but now looking at the perspective of what their crystal structures look like. And this is going to be related to the strength of the cohesive forces. So in general, ionic solids tend to form fairly well-behaved crystal structures just because we need to generate repeating patterns where cations and anions can avoid each other. So cations like to avoid cations and anions like to avoid anions. And as a result, they tend to form very predictable structures. But as we've seen, they can occasionally get a little messy. On the other end, metals contain only a single type of atom. And as a result, they also tend to form fairly predictable crystal structures, at least in their most ordered state. And this brings up an important point, is that these crystal structures can become fairly increasingly complex. However, scientists have had a lot of time to try and figure out ways to express most of these crystal structures as some sort of complicated cubic or hexagonal lattice. However, one of the big perturbations that they tend to use is they start letting the side lengths change. So instead of a cubic lattice, you have something that looks a little bit more rectangular. And you'll have things that aren't a strict rhombohedron, like a hexagonal lattice, but starts to have a bit of an angle. But once you allow for these perturbations, you can generate some sort of crystal structure that describes most salts and elemental species. However, one of the big things is if you start adding impurities, either to a salt or a metallic lattice, we tend to start deviating a lot from these regular structures. So for example, don't exactly expect bronze to follow a crystal lattice, even if copper does. In comparison, on the other end, if we start looking at molecular solids, they tend to deviate fairly easily from a lot of the predictable crystal structures because they have much weaker intermolecular forces. And it's a lot easier to have a more chaotic arrangement of atoms. These tend to, once you start deviating away from molecular solids like water that have fairly well-controlled IMFs and start working with things like plastics or sugars, where the bonds can be a little bit more chaotic, these start generating what are called amorphous solids. And they're called amorphous because they don't obey a set crystal structure. And one of the easiest ways to identify a lot of amorphous solids is because they tend to be very soft. You can bend or manipulate it. So think about things like plastic, which is an amorphous set of long chain carbon, or sugar. So if you have cotton candy, you're essentially making long sugar strands, which again tends to be fairly chaotic. And it is worth noting, they tend to have fairly low melting points. And if you heat them slightly, they can start to deform. So again, classic example of an amorphous solid is plastic. It's one of the reasons why it's so useful, because you can make it adopt any shape you want. However, one of the things that is worth noting is even if you have a material like silicates that tend to be an ionic system with a fairly set crystal structure, one of the things you can do is if you heat these substances, manipulate them, and then cool them down quickly, you can often trap them in some sort of amorphous phase. So if you take, again, quartz, so this would be sand, heat it up, manipulate it, and then let it cool rapidly, you generate beautiful glass statues. And glass is more or less an amorphous version of sand. However, this often can happen for any number of substances. One cool molecular species that tends to morph on its own is chocolate. So it turns out chocolate has a fairly regular structure. One might even be able to call it a good crystal structure. However, if you leave it out in the heat, one of the things is that it tends to manipulate on its own, and you start separating the sugars from the fats based on those intermolecular forces, and they separate in what's called a bloom. So if you ever wondered what that white chocolate rot is on your chocolate didn't go bad. Say hello to your fats, say hello to your sugars. And that's more or less what ends up happening. So we can apply a lot of the lessons of crystal structures and solid species to everyday life. However, it is worth noting that all we've done so far is tell us about who would be favorable in the end. Now, one of the things we're going to try and figure out is how spontaneous might some of these transformations be? Not just looking at enthalpy, but figure out who is most likely to form. Next time, we're going to dive in to the great topic of Gibbs free energy and spontaneity. Until then, take care.